In last video, we introduced the ridge regression, which will be useful for the giving the regularization in reduce model variance when fitting the model. But do you guys think there is a little bit just arbitrary? We just add a term with some constant. Is there any like a justification why do we do this? Actually, there is in from the Bayesian statistician's point of view. So there is a Bayesian justification for this regression. Regression, okay? So you can think this weight lambda can be think sort of the prior probabilities on the W's. Okay, so it's ridge regression. You can think it's assign a prior distribution probability on the weight, and we assume weight. We can in Bayesian statistic we can assign the prior distribution by giving the prior distributions. For example, in here we can assume this W prime follows normal distribution will be centered at 0. So this is zero vector. This is a zero vector of d-dimensional with a let's say tau square. Okay, so recall that the normal distribution with a single variance parameter will have the density like proportional to there's a constant in front, but this will be proportional to the exponential function to the negative 2 tau square W prime norm square. Okay. This prior probability mainly thinks that we should give the concentration of the W prime close to 0. So this is the variance of the tau, right? So how big of this tau indicates where do you think this W prime should be centered at 0? How far from 0? Okay. And then we have the Bayesian theorem. Not a Bayesian theorem, not a Bayes theorem. So the posterior distributions of this W given the data x and y can be written as likelihood. Likelihood is y given x and w. So if you think that distribution regression has normal error term, so this will be normal density and times w prime. W prime is here, and divided by the marginal densities of the y given x. Okay. So this is gives us a posterior distribution, but and then if we take the log after log transformation, I just show you the big idea. For detailed proofs of this intuitions, the Bayesian justification, please check the reference book. By log transformation, we have the natural log Fy given xw y plus natural log f w prime and minus so numerator we want the distribution for w, so there's no w here, right? So we can think it's just a constant, some constant c. And think this is c1. So, and this is equals to, because this is a normal distribution, this is normal distribution. So you can think this is just a negative, some, think of if you take the, for example, if you take the log here, so log cancels the exponential, you have negative, some constant term. So there's another constant times y, so constant times xw minus y square minus some constant w prime square. Okay, so minus some constant c. So maximize this function, maximize this is equivalent to minimize. So if we want to maximize this, so it's negative, so we want to, is equivalent to minimize x w minus y, okay, plus some constant times w prime square. Okay, so where this is given, so this is just the cost function for ridge regression. Okay, so actually, so ridge regression you can think is maximum log posterior, so maximum posterior distribution. A posterior so it's called MAP. You can think this is a maximum posterior distribution. The solution for this is the maximum posterior distributions mode for the weight matrix W prime. Okay, so this is just a little bit justification. Why do we do this? Why do we do the ridge regression? So this is so the solutions for the ridge regression is the same as you maximize the posterior distribution for omega. So that's the idea. Okay. And then next, I'm gonna talk about the lasso regression. But before lasso regression. But I want to give you some motivation too. So lasso regression, the motivation can be used, mostly used for the feature selection. Okay, suppose you have the real data. Let's say you have like if you have 10 variable, probably it's okay. But if you have like 20, 30, of even 50 random 50 features, and then you want to consider which variable is most important. For example, you want to predict the house price, right? There are many factors can be used for the regression to predict the house price. Suppose you have even, so which variable we should use inside our model to build our model? Okay. So the idea is what you can think, why don't we just put all the variables inside the regression function? So okay, so all features will increase increase the model variance. So the ideas and okay, so what should they do? So the idea here, we want to identify the per predictive features. And ignore them. Per predictive features in the regression setting, which means weight 0, close to 0, small weight. You can think it's small weight. For example, you do the regression, alpha equals to beta 1 x1. If this beta 1 is 5, probably you think, oh, it's an important factor. But if you have the regression coefficient, which is very small, like 0.002 x5, probably this variable is gives the per predictive features. Okay, so after we identify the per predictive features, and we ignore them, delete from design matrix. Okay, so this will give us less overfitting. Less overfitting and smaller test errors. Okay, so this idea of the feature variable selection, another popular name is variable selection. Are important in both classification and regression. Both classification and regression. But sometimes it's hard. And not easy job. Okay. Think about it. If you have like even you have 10 variables, how many models you can build based on 10 variables? So suppose you have the variable x1, x2. Suppose you have an Excel file. You have data x1, x2, x10. Okay. Which model? Even you build a linear regression. Okay. Simple linear regression. Which variable we should consider in our model? Okay. You can consider first variable, second variable, third variable, 10th variable. So we have 10 models here, right? You can also consider the first two variable, x1, x2. Okay. You can also consider x1, x3, x1, x4, and x10. So even with 10 variables, you can have as many. For d equals to 10, you can 0, 0. there are these factorial many models you could try, could create. That's a lot, that's a big number here. Traditionally, in the statistics, before this machine learning techniques, before this linear lasso regression and ridge regression, what people do is do it backward stepwise selection. What the backward stepwise selection is that it starts to include, you include a model, linear model with all the features, W1, X1, W10, X10, okay? And then you fit the linear regression and you remove the, so repeatedly remove the feature whose removal give the best reduction in validation error, okay? So for example, you try to build the model without the first feature in a model and see which one gives you the best performance. You remove the second one, you remove the last one. And then you do step by step, remove one feature at a time. And select the best one. In with the validation error. Okay, but still you have the even the backwards stepwise computational cost is O d square. Okay, you reduce the computational d factorial to the computational cost d square, but still this is requires a lot of the computational work. Suppose you have 10 variable, you need to calculate like 100 times. But if you have 100, you need to calculate 10,000 times. As nowadays we have the much more big data than the old times, so sometimes even this backwards stepwise selection still give you a high computation cost. Although you may lose some important features by doing this way. Okay, so lasso regression can be used for the variable selection. So the takeaway here is lasso regression can be useful for variable selection. Okay, so this video I just give you little bit of justifications of the ridge regression based on the Bayesian theorem, and also give you the motivations for the lasso regression. I'll continue next video to show you more details about the lasso regression.